Alright, morning everyone. So we're going to just pick up and continue on from where we left off on Monday, talking about graphics, in particular 3D graphics and processing and stuff. So if you remember, we sort of left off with this example here. Just drawing a cube, a lit filled cube or box, and a wireframe sphere. So hopefully you're all sort of happy with where we left up on that one. So you can see in this example here, we use these sort of processing provided primitives box and sphere. So box is obviously a cube, and you specify the size, and sphere you specify the radius. However, if you want to do anything more complicated than that, obviously you could go the Minecraft route and just make everything out of boxes if you wanted to. But, if you want to go more complicated than that, you might want to start drawing your own primitives. So to do that in processing, we use this begin shape idea. So you basically say begin shape, and you can specify, there's a bunch of different shapes we'll look at the moment, but, shapes can be quads. So basically think of like a piece of paper or something where you define the 4 corner points, and you make up an object out of assembling heaps of those together, a quad strip, a triangle fan, so on and so forth. We'll look at the various examples of those. And then at the end you put end shape, so begin shape, then you put some vertices, and then end shape. So if, say for example, we want to do a quad, we can do something like this. Hopefully this works. Oops. You gonna run, or yeah? I suppose it helps if I okay. Right, awesome. So I didn't actually enter anything on the screen. So there is a cube there, or a quad there rather. We just can't see it. Now this is one of the main difficulties about doing stuff in 3D graphics, that oftentimes it's quite hard to debug, because if something's off the screen, you just don't see it. It's not there either. That's right. We'll just run through it with a theoretical example. We'll come back and look at a better one later. So yeah, this is an example anyway of how you do a quad. So as I said, you define the corner points of the quad in space. You'll notice this one also we have fill. So essentially we can set the color at each point on the quad, and that will interpolate between it. Now I'm pretty sure actually there is an example in here just set up to work properly. Look. RGB cube, that's probably a good start. Yeah, so RGB cube actually does what we want to do with a bunch of other stuff as well. So this is a simple cube which goes from white in one corner, so 255, 255, 255, to black on the other, and then each corner, so you have white there, blue, red, and green, and then the colors are just interpolated between them. But if we actually look at and obviously it follows the mouse pointer, but if we look at the code, that's pretty much what we saw before. In fact, that's exactly where I copied the code from, why it's not working. And the other one, I'm not sure. But we begin shape quad, and then we define what color we want each of the vertices to be. So this one is like yellow or cyan. I can never remember which way around those two are. And then we basically specify the vertices position in space. So this one is at -1 by 1 by 1. Often when doing these sorts of things, I find it easier to sit down with a piece of grid paper or something beforehand and actually draw the shape out and figure where all the coordinates need to be in space. It's quite hard until you sort of really get the hang of it to just figure it out in your head. But basically, if we look at these numbers, they're all 1 or -1, and essentially let's see if I can fold this into a rough cube shape. Close enough. So imagine this is our cube here, and there's another side. we go from the top corner, which is -1, -1, -1, and this corner will be 1, 1, 1. So basically the origin of the cube, or the center of the cube, will be at 0, 0, 0. So going from -1 to +1 in all dimensions. So yeah, have a look at the code. I won't spend too much time on it, but it's actually pretty straightforward. We basically set up the window, and there's a little bit of code in here for figuring out the rotation of the cube. So rotate X mag, Y mag based on the position of the mouse. But really, this is pretty much everything. All the main things which are happen within this begin shape, end shape. And another thing I should have mentioned, for things like quads, for example, so obviously a quad is made of 4 points. So you have 1, 2, 3, 4. If you then start on another set of quads, or another set of points without doing end shape again, it'll just start a whole new quad. So, this is effectively the same as going begin shape, end shape, begin shape, quads. Like, it's smart enough to basically figure out that it should just start a new shape, so you don't actually have to specifically do that time and time again.
So the vertex points, that scaling those up, scale before that, so they're like -90, 90, 90.
Yep. So yeah, it's exactly as we were talking about. Good point, actually. Earlier when we were talking about transformations you can make, and how when you translate something, you scale something, you rotate something. Effectively, as far as the cube knows, it's only 1 by 1 by 1 big, but essentially by scaling it by 90, we've essentially scaled the world so that, in effect, this will actually be -90 by 90 by 90, and so on and so forth. But yeah, we can, so if I actually change this, it will change the size of the cube. Hopefully, yeah, so now it's half the size it was, and we just set that to scale of 1. This is potentially why we couldn't see it before, because it was tiny. Yeah. So, copy and paste this example, because this is possibly a slightly simpler one than the cube, but right. So here we have a little pyramid, and this one, so there's no scale in here or anything. There is a rotate, and that's just to make it look nicer, so we're not just looking at the side of the thing. So we basically set up a 3D environment, set the background to black, translate so it's in the middle of the screen, so width by 2, height by 2, turn stroke on, so we're just going to see an outline, turn fill off, so there's no texturing in it. Sorry. And then rotate it by, because remember these are in radians, so we often rotate things by pi rather than by numbers, because I think, pi is half a rotation or something in radians. And then yeah, just begin our shape. So this one, from memory, the begin shape in processing, let me just double check this actually, is effectively a line loop. Bring my mouse with me. So we'll just double check that. Shape. Yeah, so begin shape, as I mentioned before, you can pass in a bunch of different things. You can pass in points, lines, whatever else, and we'll look at that in a minute. But what it does by default, if we don't pass in any argument, is basically creates a polygon, so a complex polygon, which is closed. So here we basically define the 4 points, and it'll create a square out of that polygon. So yeah, in this one we have our pyramid, which is created. It's actually only created out of all 4. Yeah, so this one's actually a little bit confusing. It should be like that. So yeah, created out of these 4 things. So there's one here, one side here, one side here, one side here, one side here, and the base is actually just created from the fact that the 4 sides of it all share that common plane down the bottom. So if we pop that one open, that should have looked like that. And let's just say if we comment out a bunch of these, a little bit of luck. Alright, so we do need fourth side. So I can close it. This trackpad is absolutely hopeless. Yeah, so we've got part of a triangle there anyway, so it started drawing another one, and then I think it started on the other side that we can't actually see. But yeah, have a play, and specifically, especially with the examples as well. There's lots of nice examples in here. Looking at various things. Where is it? Demos, I think. Graphics. So yeah, graphics has a bunch of bits and pieces. What was it? There was one ribbons, I think it was. Yeah, so lots of bits and pieces there which can show you various things. And of course there is, so this one again is done by, what was this one done by Shapes, is it? Okay, this one's a little bit more complicated because it's actually reading the shape of it out of a file, so maybe not the best example. But yeah, there's lots of stuff in the example files which will sort of show you how to build it up. And I mean, I'd recommend sort of sitting down with a piece of graph paper or whatever and drawing out the shape you want and then trying to build it up from the primitives from there. These were actually the demos I was looking for. So yeah, we looked at the RGB cube before. Should still be open somewhere here, which basically just creates a cube out of quads, so 6 quads, one for the top, one for the bottom, one for the left, one for the right, one for the front, one for the back. Each one is colored and each one is colored a different color, so we end up with an RGB cube. Another good example. Where are we? Is vertices. So this one actually shows off sort of a cone pyramid type thing, and this is made, we'll actually come back to this in a minute because it's made of 2 different things, or 2 different shape primitives. It's made of a quad strip and triangle fan. So we'll come back to that in a minute, because I wanted to talk about basically the different graphical types you can do. So all of these are actually the graphics and OpenGL definitions, but they're pretty much the same thing in processing because processing uses very similar libraries. So if we pop back to the processing begin shape thing, they've actually got a nice little demonstration of if you call define shape and then 4 vertices, what you end up with. So just ignoring the first one to begin with. If we start off with just points, we basically just draw a single pixel at each of those points. So vertex 30, 20, 85, 20, 85, 75, 30, 75. So these ones here. So we just put a point at each thing. If we do lines, it'll basically grab 2 vertices at a time and connect them with a line. So pretty straightforward. So we'll come again, skip those because those are processing specific ones. We'll come back in a minute. Triangles, so this is now we've got 6 vertices. If we do triangles, it'll grab 3 points at a time and create a triangle out of them. So 1, 2, 3, 1, 2, 3 will be those. That will be the first triangle there. 30, 75, 40, 20. Actually, if it's 30, 75, it's that one there. 30, 75, 40, 20, 50, 75, because x values increase across this way, y values increase down this way. So 30 by 75 is a large y value, a small x value, so it's that one there. 40 by 20, and then 50 by 75, and that's the second one. So that's a triangle. Triangle strip, this is where it starts to get a little bit more complicated. So what actually happens here is the first 3, so 30, 75, 40, 20, 50, 75 are the same as what you see here. So this point here, this point here, and this point here, and that basically creates that triangle. Then what happens is for every additional vertex you add, it creates a new triangle out of the last 3 vertices. So this next one here, 60, 20, is actually this vertex here. So what it does is we say this point here, this point here, this point here, and it creates that triangle. Then we go this one here, and it'll take, so this is point 1, 2, 3, and then it'll go 2, 3, 4 to create that triangle. We add this one, and then it'll go 3, 4, 5, and then we put in 6, and it'll go 4, 5, 6, and 7, 5, 6, 7. So it basically creates a strip of these triangles as it goes along. Triangle fan this is a pretty poor example of why you'd want a triangle fan. The other one, which we'll come back to in a bit, is more interesting. But, basically the way a triangle fan works, so a triangle strip is, as the name suggests, a strip of triangles which go along in a line. Triangle fan, you actually start by defining the center point of the fan. So this first one here, 57 by 5, that actually says, by 50 will be that point there. Then what we do is we define all the points around it. So this 57.5, it's at the same x value, lower y value, so it'll be that one there. And then 92 by 50 will be that one there. So it creates a triangle using a center point and then these 2 points. And then for every additional point we have, we grab the last point and the center point. So this is 1, 2, and 3. It'll draw a triangle 1, 2, 3. And then if we put 4 in, it'll go 1, 3, 4. Then if we put 5 in, it'll go 1, 4, 5. And then 6 in will go 1, 5, 6. Sorry. So basically, as it suggests, all the triangles are fanning out from that one center point. And then quads are pretty much working exactly the same way that triangles do, except obviously they have 4 points in them rather than 3. So on this one we have 8 points, or 8 vertices. So the first one will be 30, 20, 30, or 30, 20, 30, 75, 50, 75, 50, 20. So this quad here. And then this one here, 65, 20, 65, 75, 85, 75, 85, 20 defines that quad there. So the first 4 points, the first 4 vertices define this quad, and the second 4 define this quad. Then we have quad strips, which are, as you'd expect from quad fans, exactly the same thing. So we define 1, 2, 3, 4 points, and then when we add another 2 points, it basically takes the last 2 points and the new 2 points to create a new quad. So this is 1, 2, 3, 4. We create a triangle, then we go 5, 6, and so we create a triangle out of 3, 4, 5, 6, and then we go 7, 8, and we create one out of 5, 6, 7, 8. So we just keep on tacking on quads as we go around. And then the primitive ones for processing, which is basically where you don't actually define anything in this begin shape thing, basically creates a complex polygon out of whatever points you give. So if we look back at these early examples where we had these 4 vertices which draw points, if we do that with the begin shape, it will create a square. If we begin shape and end shape with close. Now, I don't actually like this that much because it doesn't fit with the rest of the ones. Like the rest of them, you just begin shape point and then end shape nothing. But with processing, it's a little bit processing primitives. It's a little bit different. If we say close at the end, it will close our primitive up. So you can see here we've gone 1, 2, 3, 4, and then we say close, and it creates that last line there. If we, however, these two here, the only difference between these 2 pieces of code, one which draws this sort of sideways U shape, and this one here, is that this one ends with close and this one doesn't. So if you don't specify close, it won't close the line. It basically treats it like 4 lines. And down, there was one more somewhere I saw. Yeah, so down here again, if you want to draw this shape, which obviously isn't a square, isn't a triangle or anything, you can use processing's begin shape thing and define each point and call close, and it will create that. So it's obviously using processing's one is a bit more powerful than using the OpenGL default quad strips, quads, whatever else. Like if you're going to do this in OpenGL, you'd need to do it out of at least 2 quads, like one large one here and one small one here. Whereas with processing, you can do it in just one shape basically. But yeah, it's more powerful, but it's less canon, I guess. Like it's, if you go to OpenGL afterwards, you can't do things like this. Like these sort of complex shapes aren't supported by default. You'd have to create them by yourself. So if you want to use it, you know, go right ahead and use it. Makes life a little bit easier, but just be wary that if you want to port your processing code to OpenGL, you're going to have to, processing code to pure OpenGL, you're going to have to then go back and change all these primitives. So if we go back to this vertices demo again, so this was the one which basically draws this like sort of cone shape type thing. So there's actually two types of primitives which are being shown here. So if we look at it, there is this one here, the quad strip. Anyone want to take a hazard a guess at what part of the cone is being represented by the quad strip? Yep, so it's the sides here. So actually I might just turn that light out so you can see a little bit better. So if you look, you can actually sort of see each of these is shaded in its own color and the edges are flat. So essentially what we've got is each of these is just a quad, which starts off very small here and then goes out to quite large here. And basically when we're creating it, all we do is we go, okay, there's a point there, point there, point there, point there. And then once you've drawn the first one, you just have to specify the next 2 points, and then the next 2 points, and then the next 2 points, and then the next 2 points, and it'll generate that quad strip as it goes round. So if we comment this chunk of code out and rerun that, whoops. You see we've lost the sides of it, so we just have a couple of disks floating in space now. And in fact, I change that now from a quad strip to just quads. Does anyone want to take a hazard a guess at what happens if we change it from a quad strip to just quads? Yep. So we're going to end up with basically every sort of second one drawn in. Not quite right for some reason. It's probably to do with the order that they've defined the vertices in, that instead of going like alongside like that, it's grabbed like 1, 2, 3, 4 or something. So it's, yeah. But if we change the order that the vertices would come in, it would be more like you expect, which is actually what I was expecting it to come out as. But obviously, the way they've defined their vertices is a little bit weird. Actually, it looks like, I think the way they've defined their vertices is 1, 2, 3, 4 or something. So this quad is actually being like stretched out like an arrowhead sort of shape. All right, so obviously if the quad strip is the sides, then the triangle fan will be the top and bottom. And if we comment that back out again. If we have a look at the top and the bottom, particularly at the bottom, it's larger, you can basically see each of the edges around here, and there'll be one point defined in the middle, and then it makes it quite easy to draw our circle or whatever else just by going, okay, here's a point in the middle, and now just draw 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 14, 15, 16 triangles originating from that middle point. And we can increase and decrease the number of those triangles to increase and decrease the number of triangles to make it more round. So at the moment, as I just said, it was 16. So you can see there's 16 edges on it. If we make that up to say 50 or something, we'll notice that it's gotten a lot smoother, a lot more rounder, because we've just removed some of the discreteness of that. And this is actually kind of a nice little example, because it shows you how you can draw your cylinder yourself out of quad strips and quad strips and triangle fans, but it's also the way they've set it up is you specify the top radius, the bottom radius, how tall it is, and the number of sides. So you can, using the same chunk of code, we can draw our nice cylinder, our nice cone, or we can draw a cylinder. So this is where the top and the bottom width are the same. And we can also draw a pyramid just by basically saying, okay, make the top a height of, or a width of radius of 0. So instead of coming, a cone goes straight up like that. A cylinder goes straight up like that. Our cone previously went up and had a very small radius. This one goes straight up to a point, so it basically has a top radius of 0 over here. The bottom radius is 180, so it's wide around the bottom, and then it's only got 4 points in it. So if we wanted to then make it like a hexagonal pyramid, we could increase that to 6. And in here you can see now, still got the point on top, but now we've got 6 sides to it, whatever else, and obviously the more you increase it, the more like a circle it becomes. Right, yeah, and so those are the OpenGL primitives. There's if you search, there's huge tons of information about OpenGL out there. So if you go through, read some of the tutorials, particularly I know we've been doing processing recently, but there are a set of tutorials out there called MHIT. They're primarily for like C and stuff like that, but certainly the content is fairly similar in a lot of ways. You just need to port it a little bit. So these were primarily built for Windows running in a C environment, so it teaches you how to create a window and all the sort of stuff that we don't have to worry about because processing does it. But it looks at stuff, how to create polygons, which will be the same in OpenGL and processing, just the function names are a little bit different, how to add color, how to rotate, how to create 3D shapes. And then they're actually really good. They gradually build in difficulty, texture mapping, lighting, blending, bitmaps, right up to like really crazy stuff, anti-aliasing, CG, vertex shaders, all sorts of cool stuff. So yeah, I mean, it's one thing, and we'll probably come back to this when we get to open frameworks, because that's written in C, so some of these things are a bit more useful. But even beyond that, if you search OpenGL primitives or whatever, there's some nice examples which sort of show you how they work slightly better than the ones that processing provides on their website. So, if we had these vertices here, this is what the points look like. The lines connect every second point, so the arrows indicate where the lines go. A line strip, so it's just a series of lines connected to each other. A line loop connects them all, and the last one, triangles, triangle strip, triangle fan, quads, quad strip, and okay, so there is a GL polygon. I don't know that it's supported in all versions of OpenGL, though certainly I've never used it before. So is everyone happy about that? Yeah, so we'll move on. Lecture 7. Where is lecture 8 gone to? See it again. All right, so we talked a little bit on Monday about transformations, how you can move stuff, you can rotate it, and you essentially rotate the entire world effectively. So all things you draw on the screen will be affected by the current state of what's known as the world transformation matrix. So within processing, if we go, let's just start with a nice easy one actually. This code. So let's do just cut down that RGB cube example until we have a nice simple cube. Try and figure out which side is the front. There we go. Cool. Right. So now we have a nice simple example which just draws a single quad on our screen. Oops. Like that. So with in processing we can rotate things simply by using rotate and then the direction we want to rotate in. So keeping in mind, well, let's actually we'll work through them. So rotate x by 15 has rotated through the x-axis. So the x-axis runs from the left, unless you have rotated the world coordinate system. By default, the x-axis runs from the left-hand side of the screen to the right-hand side of the screen. So it's essentially rotating it around that way relative to us. Rotate y. We'll rotate it around the y-axis of the screen, which by default runs from the top to the bottom, so it's going to rotate it that way. So x is that way, y is that way, and of course that means that z will rotate it into the screen. So x, y, and then z is that way, so that's going to rotate it around that way. So these rotations are in radians as well. So if we go, they float x equals 0. X plus equals 1. So adding 1 to our rotation amount each frame isn't going to rotate it 1 degree at a time. It's actually going to rotate it 1 radian at a time. So as I said the other day, if we want to convert from radians into degrees, we have to, what is it, 1 pi over 180. There we go. So yeah, the easiest way, and the way I remember this, is radians are smaller units than degrees. So in degrees, 180 degrees is half a turn. I think from memory, I can't remember exactly, but I think a pi is 1 full rotation. So half pi is half rotation, and pi is 3.14. So 360 in degrees is 3.14 in radians. So if you want to convert from radians into degrees, you need to make it a large number. Otherwise, you need to make it a smaller number, and pi over 180 is going to be a smaller number. So if we have our number in degrees, so x is effectively in degrees, so that'll go from 0 to 360. We want that to scale from 0 to 0 to pi, so we basically multiply it by pi over 180 f, because pi over 180 f, pi over 180 is 0.01, so it's basically going to shrink the number. If we needed to convert from radians back in, we would just go 180 over pi would convert from radians back into degrees. But yeah, it's just a little aside. If in doubt, one of the easiest ways to check these sorts of things is do a simple example like this. We know that this is going to rotate at 1 degree per frame, and it's obviously not, so there's a good chance that that's actually working in radians rather than degrees. Right, so that's rotation. Everyone happy with that? Yep, so 3 axes, x, y, and z that we rotate around. Just imagine if all else fails, imagine sticking a skewer through it, like you're rotisserie a pig or whatever. Stick a skewer through it in that direction and try and imagine which way it would turn as you rotate the skewer. Translate is even simpler. So if we translate by 10, it's going to move it 10 units, which is been scaled by 90 is quite large. Do that before the scale. So maybe if I make that x. So if we translate in the x-axis, it's going positively, it's going to move to the right. negatively in the x-axis is going to move to the left. Y, so positive translation in the y-axis is going to move down. Negative translation in the y-axis is going to move up. And finally, so we can either do translate with just x and y, or we can do x, y, and z. Positive translation in the z-axis is going to move it towards us, and a negative translation is going to move it away from us. So obviously all of these are from what's known as the identity world transformation matrix. So the identity world transformation matrix is basically what it is when it's set up. If if it's moving towards me with a positive and away from me at a negative, if I rotate the entire world 180 degrees, a negative is then going to move it towards me and a positive is away from me. So essentially it gets quite complicated when you start dealing with like lots and lots of manipulations at the same time. So if you rotate, translate over and over again, you're going to end up getting quite confused, and that's why we have these push and pop functions. So we only need to change the transformation matrix for whatever we're working on. We don't need to keep on, trying to figure out, okay, I've moved here, now I need to move this little bit to get where I want to be. You're far better off starting with what's known as the identity, where this X is this direction, Y is this direction, Z is this direction, this is positive, this is negative, this is positive, this is negative, this is positive, this is negative, and returning to that, because at least you know how everything is in that state. If you rotate everything by 180 degrees, then everything's reversed, and then you have to keep that in mind whenever you're doing your transformations from there. So push and pop are absolute lifesavers. Use them whenever. Basically, if you're ever doing like a translate, a rotate, or a scale, I would highly recommend putting push for it and pop afterwards to make sure that you don't end up screwing your transformation matrix up, because then you end up with things not being where you wanted them. If you're lucky, you can still see where they are. A lot of the time, you'll rotate or transform the transformation matrix in such a way that when you draw something, it just won't appear on the screen and you have no idea what it is. And it's because you've got something here and you're trying to draw something behind it, but you've rotated the world in such a way that it's actually now behind the camera and you can't see it, and you draw it and nothing pops up and you're like, where is it? Why is it not actually showing anything? So yeah, push and pop, use them all the time. So I just missed scale as well, so let's quickly look at scale. So you can scale 90. I have a feeling actually, just need to have a look at the syntax. Yeah, so, oops, we take that translator. So, like a lot of things, processing and trying to make things simple often makes them more confusing. So if we specify scale by 90, like we just give it one argument. Like if you remember the other day, we looked at how you can have functions which have 1 or 2 or whatever arguments using overloading. So if you say just scale with one argument, so scale 90, it scales the x-axis by 90, the y-axis by 90, and the z-axis by 90. However, we can actually specify different scale parameters. So if I do it like this, now we've scaled it by 90 in the x-axis, so 1 unit is now 90 units long in the x, and then we've scaled the y by 45, so 1 unit is now 45 in the y, and the z is still at 1. So you can do some quite cool things with this. You can squash things, and here it's not particularly interesting because you're like, oh, well, I could have just done that by changing the size of the vertices. But if you have like nice 3D models, you can actually squish a 3D model without having to worry about figuring out where all the vertices are just by scaling it in a certain dimension. And you can also do, it's not going to show up so much here, but you can do negative values as well, which will actually mirror image the thing. We'll look at that in a minute.
You're going to do a 3D cube by expanding the Z.
No, so because it's still, well, if it was a 3D cube to begin with,
yeah,
like expanding the z-axis will expand it. However, if you look at this definition here, the z-axis on all of them is just 1, so it's just going to shift all of them back by 90. If they were spread out, so say we had points 1, 2 here and 3, 4 a little bit behind it, so instead of being flat like that, it was like that, it would effectively stretch it out in that dimension, but it won't make 2D things 3D. It'll just stretch them. And there's a nice example here. So, are you guys all set up on Learn yet? Yep. Okay. So I'll put my lecture material on Learn so you can have a look at it, because I try and like sort of include like like useful examples, or at least links to them and stuff, so you can go back and have a look at them. Processing. Right, so there's one here which shows the usefulness of push and pop. Basics. Transform. So we looked at ARM the other day, that's the rotating one. But we can have a look at rotate push pop, which does this one. So there's actually a ton of boxes there all overlaid on top of each other. And you see for each of these boxes which are drawn, we push matrix and then we rotate by a tiny amount, and then we draw the box and we pop matrix. And you see basically they're all overlaid on each other nicely like a cactus or something. If we comment out the push and pop matrix, those rotations are all going to add up, and we're going to end up with something far more chaotic. Because instead of rotating them each a little bit relative to the last one, we're accumulating those pushes. So arguably it's slightly more interesting to look at than the other one, because they're basically all increasing speed as they go, but you can see it's quite a different effect. And there's plenty more examples in that transform one as well, looking at various things. So another rotate example. So this one basically just rotates a cube, adds a little bit of jitter, and kind of pointless. So rotating in the X and Y at the same time, you end up with some weird effects, because so if I say, if this is X and this is Y, if I rotate in the Y dimension 90 degrees, it'll turn 90 degrees relative that way, so from here around here. But if I then rotate the X-axis, it's going to rotate effectively the other way. So one way would see it rotating in one direction, but if we rotate the X-axis in the other direction, effectively everything's mirror imaged. So yeah, you can see this is all it's doing is rotating by X and then rotating by Y and drawing a rectangle and then doing the same thing again, but because the X and Y axes are gradually rotating, it sort of, gets a bit weird. Whereas if we push and pop, it will hopefully be a little less out of control. So now, because there's no cumulative effect, the two rectangles are essentially sitting directly on top of each other. The reason you have that black and white line there is that's actually just to do with when it's rendering it, it's trying to figure out which one's sitting on top of the other one, and because they're effectively sitting directly on top, it's a 50-50 chance which rectangle is going to, or which pixels from which rectangle are going to be drawn at any point in time. So that's why it appears like the line is moving. Scale. So this one's kind of a cool one. So the one, there's two boxes being drawn here. One is just being scaled from memory, like shrinking and growing, and the other one is actually flipping negative to positive. So that's why it appears to flip. It actually looks like it's rotating around one side to the other, but actually all that's happening is it's offset and then it's getting smaller, and as it goes to 0, if we say, let's translate out by 10 units and draw a square there, as the scale approaches 0, that 10 units is eventually going to become 0, so it's going to move into the side, and then as it goes into the negative, we start actually scaling out the other side. So if you look there is a translate here, but it's always positive 75, but as the scale goes into the negative, it will actually flip that from positive 75 to negative 75, so it appears to be swinging from one side to the other, when in reality it's actually just going, like the scale is going from flipping from positive to negative. And translates, which is one, wow, I almost showed you that car demo the other day, and this is kind of similar, except this is looking at how translations and stuff accumulate, as we've talked about time and time again. So let's restart that. Basically, we translate x, and then we draw a rectangle, and then we translate x again, so we're only translating as far, but because we're adding x and x effectively, we end up with two rectangles, which one is moving twice as fast as the other one. Right, and this is basically the math behind it. So you guys aren't expected to be able to follow this, but if you're interested, this is basically how it works. So if we have our x, y, z position for each point in our object or whatever it is we're drawing, or our scene, we have x, y, z, and we want to find where their position x prime, y prime, and z prime are going to be after the transformation, or the translation rather. The translation matrix looks like this. So we have our terms tx, which is the translation in the x axis, ty, which is translation in the y axis, and tz, which is translation in the z axis. And if you basically multiply this matrix by this matrix, you end up with that, which is effectively, if you collapse it down, x prime is equal to x plus tx, y prime is equal to y plus ty, z prime is equal to z plus tz. So that one's pretty straightforward. The reason we show it like this is because when we look at rotation in a minute, it gets a bit more complicated. So same thing here with scale, except this time, instead of these three parts of the matrix being tx, ty, tz, we have these here, which previously were 1, 1, 1, 1, and these basically sort of defined the scale of the axes in the world transformation matrix. Then our sx, so the scale in x, sy, the scale in y, and sz, scale in z. And if we write them out in just algebraic form, it's x times sx, y times sy, z times sz. And that will scale around x, y, and z. And rotation's coming. So yeah, as I mentioned, there are different types of scaling. So if our scale value s is greater than 1, we'll stretch it. So we saw before we had that cube which we drew it 1 by 1 by 1, which ended up being 1 pixel. As we set that to 90, it stretched it from 1 pixel out to 90 pixels by 90 pixels by 90 pixels. If we set the scale value to 1, it's going to remain at the same size that it was, because that's what, if you look at these here, it's normally 1 by 1 by 1 in that diagonal, whereas here it's sx, sy, sz. So if we set it to 1, we end up with what we started with. If we set it to a number, s to a number between 0 and 1, we're going to shrink. So if it's 0.5, it'll be half the size it was, because obviously multiplying anything by 0.5 is half, so on and so forth. If we set it to 0, we decimate it. So basically, if anything has a scale value of 0, so 0 across here, it will effectively end up as 0. Anything multiplied by 0 is 0, and nothing will be rendered. Sorry. If we have a number between 0 and -1, we reflect and shrink it. So, if it's, say, 1 pixel this way, if we multiply it by -0.5, we're going to end up with -0.5. So it's effectively anything which is drawn out in this direction will now be in this direction, but smaller than it was. If it's set straight to -1, it'll reflect it. So if these were -1, -1, -1, we'd reflect in that axis. And S of greater than or less than -1 rather will reflect and stretch. So if we had our box before where it was 1 pixel, we stretched out to 90. If it would have done -90, it would have been the other way around. So if this corner here was blue, this corner here was yellow, when we multiplied it by negative, we'd have yellow on the left. Sorry, blue on the right. Ugh. So yeah, using scale, we can do some nice reflections. So if we set y to be negative, so this value here becomes -1, we will reflect around the x to z plane, so this plane here. So this boat here, down the bottom, what it normally looks like, or either of those actually. So let's say we draw this boat. If we then go scale by 1, -1, 1, we will turn this boat into that boat. If we do the same thing in the x-axis, then we will flip the boat from facing in the left direction to facing in the right direction. So, you can imagine if you have a game with 3D models or whatever, you got a little two-dimensional platformer, you want to turn your 3D model of the guy running to the right to the left. You don't have to create separate animations or whatever for him running in the left direction as the right direction. You can actually just multiply the scale value by -1, and all the animations you've done of him running to the right will then appear like he's running to the left. So you can actually save yourself a lot of trouble just by, learning how to reflect things using scale. Cool, everyone happy? Yep. Sorry. Right, rotation. This is where it starts getting a little bit more complicated. So this is, again, our world transformation matrix. So y is positive in the vertical direction relative to the screen. X is positive in the horizontal towards the right. And Z is effectively poking out of the screen towards us. So rotating in the Z direction is like we're sticking a skewer right through the screen and rotating everything by that. So if we rotate this triangle here by Z, and it's always rotated through this origin as well. So we're not going to rotate on the corner of this triangle, we're not going to rotate through the center, we're actually going to rotate through this axis here. So if this triangle is sitting out here, as we rotate, we actually rotate it right up and around. So you see we've rotated the whole thing off that. We'll look at how we can rotate through various points of objects later on. Basically, so we rotate Z around theta, and actually have the full matrix drawn out, but basically this is what it looks like. So x prime, if we want to figure out where the new x, y, and z value is for every point in our scene, x prime will equal to x times cosine theta minus y sine theta, y prime is x sine theta plus y cosine theta, and z stays as z. So obviously you can see this z position, the z position at this point here is the same as z position here, and so on and so forth. So z stays the same. X and y change by cosine theta, sine theta. And if you look at this matrix here, you have, as I think, you have cosine theta here, negative sine theta here, sine theta, and cosine theta there. I forgot to put the actual matrix form in, but yeah, cosine theta, negative sine theta, cosine theta, in case you're interested, which I'm sure nobody really is, but that's fine. The rotation about the x-axis, it's pretty much, if you look at the two of them, they're pretty similar, except here we had y and z, here we have z and x. So, here we have x and y, here we have y and z. So if we rotate around the x-axis, so the line running parallel to our screen, so like sticking a skewer through the side of the screen, rotating back and forward that way, the x values always stay the same. So this x value here is the same, this x value here is the same, but the y values have changed, the z values have changed by cosine, negative sine, sine, cosine. Rotation about y, so now we've got the skewer up and down through the center of the screen. As we rotate, they rotate around this way. The y values still stay the same, so the y value from 0 to here is the same as there. That value there is the same, there is the same, but everything's rotated around that way. And again, cosine, negative sine, sine, cosine, but this time it's z and x. So it's, you notice if you rotate around z, z will always be the same, and then it's cosine, negative sine, sine, cosine. If you rotate around x, x is the same, cosine, negative sine, sine, cosine. Rotate around y, y is the same, cosine, negative sine, sine, cosine. So pretty much the exact same formula each time. It's just you're changing which ones you're affecting, whether it's, if it's x, you're going to do y and z. If it's y, you're going to do x and z. If it's z, you're going to do x and y. This is where it gets a little bit difficult. So the order of the transformations is really important. So you saw before I kind of screwed up when I typed that code out. I was looking at trying to translate something. So I was trying to move it across by, 10 pixels or whatever it was, and it just disappeared off the screen because the line before that said scale by 90. So when I was trying to move by 10 pixels across the screen, effectively that 10 was being multiplied by the 90 to give us 900 pixels, so it had shot right off the side of the screen. And to fix that, basically all I did is move that line one before that. So this is one of the things which is probably one of the hardest things about 3D graphics programming. You just got to try and make sure that you do things in the right order, because if you do them in the wrong order, you get the wrong results and things get really confusing. So in this example here, we have this arrow, and in one we rotate it and translate it, and the other we translate it and rotate it. We use the same values for the translation and rotation each time. It's just basically one we have rotation first, then translate, then we have translate and rotate, and we end up with quite different examples. So it's not as obvious here, but certainly depending on the magnitude you use, you can end up with huge differences. So in this one, in this one we have our arrow pointing up this way, then we perform a rotate. So we rotate again, as I said before, we always rotate around the origin of the world. So we rotate around there, we end up with that, and then we translate it across, and we end up with our rotated thing rotated around the center of its base that way, and we end up pushing it out that way. Here we do the translation first. So here in the top one we rotate then translate. Here we do the translate first, so we move this out. Except now when we rotate around the origin of the world, we're not just going to rotate around that point there. We're actually going to rotate this entire arrow around that point. So you see here we rotate here, and that point is still sitting on the origin of the world, or on the x-axis rather. But now when we rotate it, we actually rotate it relative to that point. So instead of sitting on that line now, it's actually sitting, floating out in space. Right? Everyone understand why that's happening? Yep. So when we do, well, basically if we look at that formulaically, what happens is we have our x, y, z coordinate. We multiply it by the first transformation. So in this one, it would be our rotation, and this one would be our translation. Then we do the second transformation, which is our translation or rotation. And then we do our third one, so this could be a scale or whatever else. But it's very important the order that these things go in, because you'll end up with very different results depending on which one. And again, as I mentioned before, this is why things like push and pop are really important, because these things will gradually accumulate. And in fact, if we go way back to these ones here, the world matrix, by what's known as the identity matrix, is this, except this is 0, 0, 0, so it actually looks... So the world matrix actually looks like, just want to edit that one. So this matrix here, 1, 1, 1 in the diagonal corners and zeros everywhere else. This is what's known as the identity matrix. So when you start your program, this is what the world matrix looks like. The zeros, basically these zeros and these two zeros here, these two zeros here, and these two zeros here imply that there is no rotation. Because if there was a rotation, these would not be 0. These ones diagonally mean there is no scale effect, because if these had been scaled, if they were larger, they'd be greater than 1. If they were smaller, or if it had been shrunk, they'd be less than 1. If they'd there was a reflection, they'd be negative. These 3 zeros over here imply that there's been no translation. So if there'd been a translation X, this would be non-zero. Translation Y, this would be non-zero. Translation Z, this would be non-zero. And these numbers down here are just, if you guys are interested, I can tell you about it later, but basically it's just to make sure that we're talking in three-dimensional space, and this is defined as a point. If this was a 0 here, this would be a vector. But really, it's the top 4 by 3 rows which define what's happening in our world matrix. And as we see, as we see in the side here, when we multiply, these matrices, so we do a push, a rotate, whatever else, we're not just changing the, delete it, that's pretty crap. We're not actually just changing the value of the pixels, we're actually changing what's in that matrix. So at any point in time when we're doing 3D graphics, we have one of these matrices here, which is the current state of the rendering transform. So for every rotation, every scale, every translate, every whatever we do, we actually modify our copy of this. And the easiest way to get it back is to store the current state using push, and then restore it by using pop. So yeah, I cannot emphasize the importance of those two commands enough. Like they're the difference between it being really quite easy and incredibly challenging. Yeah. So if we want to rotate around a pivot point, so I mentioned before, when we rotate, for example, around this one here, rotating around the z-axis. So we'll just finish this last slide and then we'll have a break. If we want to rotate around the z-axis, we always rotate around the origin of the world. So if this one is sitting off the z-axis, we're going to rotate it around here. So it's actually going to rotate like that rather than rotating like that, which might be what we want to do. So in order to rotate around a pivot point, so we have our triangle here, normally would rotate around this point and the whole triangle would rotate around. But if we just want to rotate the triangle around that point, we can do something like this, which looks pretty intimidating, but really all that's happening is we have a translate, so this is the translate here, a rotate, this is the rotate, and another translate. And essentially what we do is we translate our entire object so that this point here, xp, yp, zp, ends up moving back to the origin of the world. So we grab it, we pull it back here, then we do our rotate, and then we push it back where it came from. So that's pretty much, if you want to rotate around the point of an object, you figure out what point you want to rotate it, do the whatever manipulation you need for that point to end up at 0, 0, 0 in our world coordinate, rotate it, and then translate it back with the inverse. So see x, y, z, negative x, negative y, negative z, we'll put it back where we came from. So we just move it to where we want it, rotate it, and then move it back. Cool? Happy?
Why is that?
Because we've basically, so if this distance is x, y, x, y, z, we want to move it so that equals 0. So x equals 0, y equals 0, z equals 0. Yeah, well, they should, according to this, these should actually be flipped the other way around. But yeah, so basically the important thing is that these two will be opposite. In this case here, if this was actually x, y, z, then this should be negative x, negative y, negative z, and this would be x, y, z. That was just a screw up on the slides. Actually, it has a correct up here, so pay attention to this one, ignore this one. Yeah, so negative x, negative y, negative z, rotate by theta, and then x, y, z to put it back where it came from. All right, we'll have a little break there, and then we'll continue on in about 10 minutes or so. All right, so, yeah, so, if we want to do rotations around a pivot point or whatever, we have to do all these independent transformations. We have to do a translation, a rotation, another translation to get back to where we were. We end up with the sort of problems that, and we've sort of covered this already, but you end up with, like lots of different transformations to model every object in your scene. So, you know, say you're making a 3D game or whatever, and you've got like every object in the game. So say you guys played Far Cry or something like that. Yeah. So, you know, Far Cry, you've got thousands of objects. You've got trees, you've got buildings, you've got vehicles, you've got enemies. Every single one of those, and even within a single object, like, you know, I'm not 100% sure about Far Cry, but you look at things which have like model-based or skeleton-based animation. So, you know, enemy characters can lift a gun, and so when they run, it's sort of independent, and then you have a separate transformation for each bone in their body and all this sort of stuff. And you can imagine trying to figure out how to translate each of these things relative to every other object in the world becomes an enormous amount of work. So, yeah, because these transformations accumulate. So, I mean, there's a few different solutions. You can reset the matrix to identity. So remember, we just looked, and the identity matrix, you have zeros everywhere in the matrix, but ones running down that diagonal. So you could do that. You could undo the transformation by multiplying its inverse, which is what we just did for rotating around a pivot point. So we translate by x, y, z, and then we translate by negative x, negative y, negative z to get back to how we were. Or we could use a stack, which is essentially what we do when we look at the push matrix and pop matrix. So we do a translation and a rotation in the real world, and CT, if we assume CT is our current transformation, we have CT equals T times R. So our current transformation will be a 4x4 array like we've seen over and over again with the ones and the zeros, except now it will have some values in that final column for the translation, and the stuff in that 3x3 matrix in the middle will have been modified by the rotation. If we then do a push matrix, what we do is we basically save the state of the transformation as it is in a stack. Have you guys familiar with stacks from computer programming and stuff?
Not exactly.
No? So basically, a stack in computer science is exactly the same as a stack in the real world. So I don't actually have anything I can stack here. Let me grab some of these. Oh, even better. So, you know, the idea behind a stack, so very, very quick computer science rundown, is if we start with nothing, we can push something onto the stack, and so that's called a push, and we have a pop where we remove it from the stack. The idea behind the stack, though, is it's a first in, first out thing. So if I push that, and then push that, and then pop it, I take the top one off the stack. So, you know, in what we're doing here, we have the current transformation, which is a translate and a rotate, and we push that on the stack, and then we have another one on top of that. Then when we, you know, in this one here, we do a scale, so current transformation now has a transform, a rotate, and a scale in it. We draw our cube, and then when we pop the matrix, we actually take that current one off, and we end up back where we started. So if this is doesn't work. So if this is our identity matrix, this is identity plus a transform. This is identity plus a transform plus a rotate. Identity plus transform plus rotate plus scale. So let's just say I have my identity matrix, and then I call push matrix, and then I do a transform, and then I call push matrix, and then I do a rotation, and then I call push matrix, and then I do a scale. And then what I can do is I can pop matrix, and then I'm back to where I was before. The rotation, pop matrix, back to where I was before, and pop matrix again, and I end up way back at the identity. So you basically put stuff on top of each other, and then you can pop back to go back to any state you were, but you have to work your way back down the stack. The difference is obviously a queue where you have things like this, and when you take things off the queue, you take them from the beginning rather than the end. So that's the difference between stacks and queues. They're two of the sort of primary data structures in computer science. But yeah, so we have the transformation stack. So basically we can work our way back from where we were back through all the transformations one by one if we want, and end up back where we began with. So, for example, this is actually one of the assignments. The last group or this first semester's master's students had to do was basically draw a house, and the house had to have a door and a window and so on and so forth. And the idea was that when you draw your house, you should have like a separate method to draw a window, you should have a separate method to draw a door, and your house should have at least one door, at least 3 windows, and so on. So rather than for each window going, okay, the coordinates for this window should be, top left is here, top right is here, blah, blah, blah. You basically have, okay, well, a window looks like we have a point here, and then there's a point here, a point here, a point here, and then you just translate, draw your window, pop back to where you were, translate, draw your window, pop back, and that way you can really easily, draw as many windows as you want, and they're all relative to the thing, to the origin of the house. And then I made it another level of difficult and basically said, okay, now that you've drawn one house, draw an entire city of houses using the same design. So it's like those little suburbs in London where every house is absolutely identical. But you end up with, you figure out how to draw it from a sort of top-down level. So you say, okay, we have a window. This is what a window looks like. And then we have a house, and a house has 3 windows in this position, that position, this position. And then you say, okay, a city has a house here, 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 and at each level, like the city has no idea where the windows need to be. The windows know where, the house knows where the windows need to be relative to that. And so you sort of end up building this categorical thing we have. Here's a city, in a city we have a house, in a house we have a window, and at each point, the transformation stack at that point only needs to know about itself. So the window doesn't care where it is in respect to the house. You wouldn't say, So here's my awesome house. This window here doesn't need to know whereabouts on the house it lies. All it needs to know is its own size and perspective and everything else. So that way we basically say, okay, well, a window should look like this. Window should look like that. And then the house is responsible, at the house level, we're responsible for saying, okay, well, the first window should start at this point. The second window should start at this point. And then we just call it, and the window will just draw it. So we update the transformation and then draw the window. And then for the city, it's the same thing. Each house doesn't need to know where it is in a city. The city just needs to know where to place all the houses. So, and by doing that, you end up with this, the idea of a transformation stack sort of comes naturally. Like each thing only needs to know where it is and things that it contains is. So the house knows how to translate to put a door, but the door doesn't know where it is with respect to the house because it doesn't really matter. All the door needs to do is look like a door. It's the house's job to figure out whereabouts on the house the door should go, and the same thing with the windows. So try and get something in your assignment to allow you guys to have a play with this. Make sure that you're doing it correctly. When you define an object, you only define what the object needs to know. You don't, you could theoretically say when you're designing this house, if this is 0, 0 here, you could have a method draw window 1, and draw window 1 draws the window starting at -10 by -30 or whatever, and then you have draw window 2, which is 10 by 30, and it does it each. But then as soon as you want to add another window, you have to figure out the coordinates on the house for that window and so on and so forth. Whereas if you just basically say, okay, well, this is what a window looks like, and then we'll just, when we go to draw it, we'll move the transformation to that point, and then just say, draw a window here. It makes it a lot easier, a lot more flexible. There is an alternative to using push and pop matrices, just to let you guys know, because this has come up in previous talks. There's also the idea of a scene graph. So a lot of things these days are choosing to go the way of scene graphs. So if you're doing stuff in C, you can use Open Scene Graph or OpenSG. If you use something like Unity, they have the idea of the scene graph implicit inside it. I'm sure things like Unreal and a lot of these other game engines have the idea of a scene graph as well. And basically a scene graph looks something like this. So instead of, drawing things one after the other, so you say, okay, let's draw a city. Okay, to draw a city, we have to draw houses, so do this in this order. You actually have this data structure which looks sort of like this. So you start with your scene root. So this is again, the idea of a house. So we have our root, which is basically everything comes from the root. and then we transform from the route and we start to draw our terrain. So, you know, houses or trees, bushes, all that sort of stuff. So from our terrain, you know, if we start from nothing, we move somewhere, and then we start drawing our terrain, and then from our terrain we move and draw a bush, and then we go back to our terrain, and from there we move and draw a tree, we go back to our terrain, move and draw a bush, and when we draw the house, you know, so we might say, okay, well let's draw our terrain over here, so we'll draw trees and bushes here, and then let's move to a certain point and start drawing our house. And then when we're going to draw our house, we're going to transform, and we're going to draw a window, so we're going to move up here, draw a window, move up here, draw a window, and then we're going to transform to here, draw our door, and then we're going to transform, draw our door handle, and then maybe we have a heads-up display or something else in it as well. So the idea behind a scene graph is that every node in it affects all the nodes underneath it, but only the nodes underneath it. So this transform affects everything in here. So if I moved this, all our bushes and trees and terrain and everything else would move, but our house would stay where it is. If I moved this, if I updated this transform here, the door would move, the door handle would move, everything would move, but it wouldn't affect the house, it wouldn't affect anything else. So it's only the objects underneath it in the scene graph, in the tree, are the things which get manipulated. And this is sort of, you know, what you end up kind of designing yourself when you're doing something like design this house. You go, okay, so I have my house and I want to transform and draw a door or a window over here, but instead of like sort of having it in this nice data structure which handles everything yourself, you'd go, okay, house, push matrix, transform, draw window, pop matrix, push matrix, transform, window, pop matrix, transform, push matrix, transform, door, so on and so forth. So the idea behind a scene graph is it's just basically encapsulating that idea of saving the current state of the world matrix, doing some stuff, and then returning back to where you were. So it sort of just takes care of doing all that push matrix, pop matrix, stuff yourself. Sorry. Anyone have any questions about that? No? Maybe? All right. And just do a little bit of the next lecture because it carries on anyway from there. Right, so programming and graphics. So we've looked at how we can draw primitive objects. So, you know, we looked at boxes, we looked at spheres, we looked at how we could construct stuff out of points and lines and quads and triangles and so on and so forth. However, there's a lot more to 3D graphics than just that. So so far we've been relying on how processing sets up its 3D environment and stuff like that, but there's more to it than just what we've looked at. And mainly that comes down to things like how you take these objects in 3D space and you render them to a 2D window. Because, you know, we looked at how you have the X and the Y and the Z positions of objects and points and vertices and everything. And, you know, that's all very well when it's abstract and it's inside the computer. But somehow, eventually, we need to figure out how we're going to draw all those 3D points on a two-dimensional screen. And so that comes down to the idea of having a camera. So the 3D graphics has sort of taken a lot of its ideas from things like photography, photogrammetry, all these sorts of things. So we have some 3D environments. So in computer graphics, we have our 3D model of whatever we're working on. In the real world, we have a 3D world. And then on when we're doing graphics, we render that to a two-dimensional display. And that's pretty much regardless of whatever sort of format. So on a computer, now we render it to the screen. On something like the Oculus Rift, we render it to the two screens, which then get passed through some lenses. Google Glass has a screen. Most things these days, there's very few true 3D displays. They're usually 2D displays that we just render 3D stuff on. So yeah, we have this, and in photography, obviously, like if you have an old style camera, you have film, you print out a photograph. It's a two-dimensional representation of the 3D world. You know, you look at a photograph, you can't actually reach in and touch stuff. When you move your head around, it doesn't change. It's a static view. Or if it's a digital camera, you end up with a JPEG or whatever, which is the same sort of thing. So you end up with this idea that we have a camera that is looking into some 3D environment. So we have our 3D objects and stuff. We have our camera, which is our perspective for where we're looking into it. The camera has what's known as a view volume, so that's basically what the camera can see. So if I say the camera on my cell phone, for example, it has a view volume which goes out and sort of like a pyramid in front of it. However, it can't see anything behind it. It can't see anything out of that pyramid. So if I put my hand up here, it's outside of that pyramid, which is coming out from the camera, so it's not going to see it. Then we have what's known as the clipping plane, which is essentially our two-dimensional plane that we draw all our graphics on, or when we take a photo, this is what we are able to capture within that photo. So in processing, we have this function called camera, which allows us to set up the camera. And it comes with a whole bunch of different arguments, so 9 different arguments. So we have the eye position, the look direction, and the camera rotation. And when you think about it, it's actually not that hard to imagine. So say I want to take a photo of you guys. So the first thing I have is the eye position. So that's where I decide to put my camera. So I might want to put my camera here. I might think, oh, okay, this might be better over here. So wherever I position my camera in the 3D world is effectively the eye position. So as I move it around, we're updating the eye position. The next one is the look at direction, or usually called the eye look at direction, and that depends on where my camera is pointing at. So I could say here, and my eye position might be the back of your laptop, for example, because that way I can fit all you guys in. Alternately, keeping the camera in exactly the same position, so the exact same eye position, camera position, I could decide that the point I want to look at is over there. So I might say, okay, my eye look at point is that there. And so even though the camera is in exactly the same position as it was before, it's now pointing in a completely different direction. It's looking at a completely different thing. So you can see we can move the camera around, and we can, move what the camera is looking at, and we'll end up with different pictures. And even it works in the other way as well, keeping the camera in the same position, moving the eye position will change our picture. Keeping the eye or the look at position in the same thing, but moving the camera is going to end up with a different photo as well. So things are going to change if we change either of those things. And the last one is the camera's up direction, which basically defines the difference between taking a photo like that and taking a photo like that. So I can change how the camera is oriented within the world, and it will change things as well. So there's a nice little example in processing. Which shows how some of these things work. Oh, too far. Just want to see the bottom of the slide. Move I. So again, if we go into our basics example thing, you see there's an entire folder for cameras. So it's got move eye, orthographic, and perspective. So we'll start with move eye. So you can see here we have our camera thing. So if we just look at it quickly, set up the size and P3D, because we work in 3D, turn on some lights, set the background, draw a box, we draw some lines, and so on and so forth. But what we're looking at here is this camera. So we have our IX, IY, IZ, our center X, center Y, center Z, which is our look at point, and our up direction. Now the up direction is what's known as a unit vector, so it's a vector of length 1. And basically it defines which way the camera should be oriented vertically. So in this case, we've said the Y direction of the camera. So if this is, let's say this is X, X, Y, and Z going through this way, we've basically said that Y, so 1 in this direction, a vector going in this direction is the up thing on the camera. If I said that X, or X with 1, should be up, then the camera would effectively be like me holding the camera that way instead. But yeah, sorry. When I say this is a unit vector, basically these things have to sum to 1. And typically, sorry, most of the time you're going to see something like this, 0, 1, 0. But you could, for example, say, okay, well, if this is 1, if 1 in the Y is this way, 1 in the X is this way, I could say 0.5 Y, 0.5 X, and we'd end up with a vector pointing in that direction, which means that the camera would be effectively being held at that sort of orientation. So in this one, basically the camera's Y position, so it's sitting out here, and I can adjust the Y position of the camera this way by moving the mouse up and down. and you can see that actually has quite a significant effect on what we end up seeing. What we end up seeing in the thing. So we're looking at an object like this here, and the camera's sort of sitting out here, and then basically I'm moving the camera down, but because it's always looking at the same center position, it's actually effectively like moving this way, because it's always got to keep looking at the same thing. So as we look at it, the camera is coming down like that, and that's what we're seeing here. We look at the front of it, so when we're sitting front on, and then as we move the camera down, we're going to start coming down like that and getting this extreme underneath sort of shot. So we come down, 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 and we're looking like that all the way down. Cool? Happy? The Z. So in this one here, X, Y, Z. In the camera up. So do you mean if I change that like that? I have no idea whether we'll even be able to see anything. Oh no, there we go. Good. So it goes all a bit wild. So basically, it's not a perfect facsimile for this, but essentially, if you're saying that this camera, its up position would be like that, but yet it's still actually able to see the object as it's moving down. So yeah, it gets a bit weird. Gets a bit weird once you start changing the up angle. And to be honest, most of the time you're going to see something like that. Really, that the Y direction of the camera is up, because effectively what we've done there is we've sort of somehow turned the camera on the side, but this camera is able to still see off the side of it. So when we move around, it does this weird twist and everything. But even despite doing that, the camera is still moving in exactly the same. The camera is still just going up and down like this instead of like that. It's just when it's like that, it goes kind of weird when it does that first little bit. It has the view of the camera of the object twist quite rapidly.
Does the RPX make any difference in this?
I won't change it to a portrait image because we've defined the window to be that thing. But essentially, you can imagine, so if we look at, so you're just going to have to use your memory for a second here. So okay, so we've got the, if I turn this around, it might make it a bit easier. So we've got the thing, we've got sort of the light side there, and as we go around, we're looking at the grey side, or the darker grey side, the less lit side. If I then change that, to the x-axis, then you'll see we're looking at the light side goes to the grey side. However, if I rotate that like that, now we end up looking at the same thing as we've done before. So it is, as you said, it is effectively like changing it from portrait to landscape, except the window and everything stays the same. So everything stays the same apart from what the camera is doing. So yeah, if we actually rotate the laptop, so we're effectively doing the opposite of doing that, and you can see that you're actually seeing what you would see if you had oriented it in that form. Right, any other questions? Okay, so that's a camera. It's kind of nice because we're used to working with cameras. We can sort of understand what changing various bits and pieces of them means. There's also the idea of a view volume, which is a little bit less intuitive because it actually allows us to do things which aren't possible in the real world. So have any of you guys ever done like any engineering or technical drawing, like drawing plans for a house or anything? Yeah. So, if you've done like computer graphics projections or like drawing. Yeah. So you probably have actually come across orthographic, in which case it'll make more sense to you than somebody who hasn't necessarily done anything with it. So the idea is we have various projections we can do things in. So we have the perspective projection, which is what we experienced in the real world. And the idea of perspective projection is, as things get further away from us, they sort of all tend to converge or diverge to a point. So, if you look at two parallel lines, like, in fact, the perfect example is usually that. So this is this looks perfectly normal to us. These two lines, these railroad tracks, are converging into the distance. We know they're parallel lines because otherwise the train would launch off them. So they run perfectly straight. But for us, the way our eyes work and everything, we see them appear to eventually converge at a point at distance infinity. Everything converges to this one point. That's known as a perspective projection. That's what we've been seeing so far in all the examples. There is another type of projection which is commonly used in like engineering drawing and stuff like that, which preserves the idea of parallelism, collinearity, all these sorts of things, which is called an orthographic projection. Probably the best way to describe that is for you guys to see it. I don't know why that changed the view volume, but this is a perspective view of a box. So if I just grab a couple of these pads here. So we know that this is a cube. We know that this line here and this line here are parallel. However, if I line these up, we can see that it's not going to take long for them to actually converge to a point. This is a perspective projection. This is an orthographic projection. That line and that line are parallel. That line and that line are parallel. Those two lines are parallel. Basically, everything is parallel to everything else. You might have seen games and stuff which do orthographic projection. It's kind of a neat little art style. But yeah, used a lot in engineering drawings and stuff like that, because you can look at that. Like if you look at a perspective of a house, it looks correct, but it's really hard to take any measurements off. You're like, is that actually supposed to be parallel to that, or are they like slightly converging? Whereas if you look at a picture of a house like this and everything is parallel to everything else, you can actually take out a ruler and measure things and go, oh, okay, well, these two lines are obviously parallel. This house is actually not sinking into the ground or whatever. It obviously wasn't built in Christchurch. And the other thing I think this one shows is it also allows us to adjust what's known as the far clipping plane. So in reality, our clipping plane is effectively infinite. So you can see, with the exclusion of things occluding you and the horizon dipping off and stuff like that, we effectively can see an infinitely far distance, depending on how good your eyes are. Although in reality, things like atmospheric conditions, fog and smog and whatever else tend to blur that away. In computer graphics, we can actually define what's known as the far clipping plane. So we can say, okay, well, our camera can only see this distance. And so what you can see here is this is with the far clipping plane set quite far away. As I start moving it towards us, objects which are further, like the further away things are from us, they start getting deleted. So this is like that corner is the closest thing on the screen to us. That's the closest thing. And it's a similar sort of thing in perspective. It just probably looks a little bit more realistic in perspective than orthographic, because we're used to seeing things in perspective. The main reason people usually deal with clipping planes and stuff is because if you don't have to draw it, you save computation time. So if you're doing something like Far Cry and you have an island with 1 million trees on it, if you have to draw every single one of those 1 million trees, which is each one is made up of 10,000 polygons, you're suddenly looking at what's that, like 10 billion operations that your graphics card has to do. Well, 10 billion polygons, and each polygon is made of 3 points. So you're looking at 30 billion computations your graphics card has to do. So by defining a clip plane, we can say, well, at this sort of distance, a tree is going to take up like 2 pixels on the screen. So we probably don't need to render, 10,000 polygons, which are all going to condense down to 2 pixels. So let's just say, here's the far clipping plane. Everything beyond that would just disappear. With games and graphics cards and everything these days, it's not usually a problem. If you go back and play some games from like the 90s and stuff, you'll notice quite often that you'll be like playing a 3D shooter and then all of a sudden something will suddenly appear in the distance. That's usually because the clipping planes are too close. because computers weren't so good then, so they had to make them a lot closer than they do now. So you're running along, and then all of a sudden something just appears in the distance. It's because it's finally moved closer than the clipping plane, so it'll actually be rendered. Right. And then there's the perspective. So there's the perspective projection, which is what we're used to. We can create a perspective projection in processing using this command here. So we define a field of view, or the Y field of view. So, how far, if we think about this pyramid coming out from our camera of what's visible, like how far its Y field of view is. So, if it's 30 degrees, it can only see like that. If it's 40, 50, 60, so on and so forth. The wider the Y field of view is, the more you can see. However, the weirder things start to look. Like, I've found usually up to about 90 degrees is all right. If you start going beyond that, things start getting compressed and they start looking really quite strange. Then you have the aspect ratio, which is the width to the height of the camera. So, if your camera is 320 by 240, then I can't factor that down in my head, but your aspect ratio with 320 divided by 240. And then you have your near and far clipping plane as well. So we've already talked about the far clipping plane, and we typically have a near clipping plane as well. Again, it allows you to crop out a bunch of stuff which you might not be interested in. And I'm sure every one of us has played a really terrible platformer, like the old Tomb Raider games used to be shocking for it, where the camera would swing around and there'd be a wall, and you'd just be like looking at the wall like this, and you're like, okay. And then Lara would fall off a cliff and die. So yeah, it's quite quite useful to have a near clipping plane as well. So you can say, okay, well, we're only going to worry about objects which are at least a meter in front of the camera. If they're any closer than that, we're not. It's just going to completely block our view anyway. And we end up with the view volume, which is what we've been talking about, which is this volume in here of which anything within that volume gets rendered. This is how we set up an orthographic projection. So with an orthographic projection, we actually define the left, right, top, bottom, near, and far prism or cubic style object of whatever happens to appear in this volume is going to be rendered. So similar sort of thing with the perspective projection, because it's got perspective, it diverges as it goes. So we define that by the field of view and the aspect ratio. Here, because it's a linear thing, we define it by the left, right, top, and bottom. So we have basically two types. I think there are other ones as well, but certainly you're not going to run into them very often at all. There's mainly orthographic and perspective, and to be honest, 90% of the time you'll be working in perspective. If you work in 3D graphics tools, sometimes you'll see they have an orthographic option, so that it makes, even especially things like if you're working a 3D modeling tool, they often have an orthographic projection because it makes it easier to align objects. So if you look in perspective, you sort of look at it, and if they're off by a little bit, you're like, it looks close enough. But if it's an orthographic, it's pretty obvious that they're actually not sitting right next to each other. And then we regardless of whether we're using an orthographic or a perspective view, we can change our camera, or orthographic or perspective viewing volume, we can change our camera view by using the camera. Cool? Everyone happy? That's about all we're going to talk about with cameras. And we've got 10 minutes left. Look. Yeah, we'll probably end it there, because now we're going to get into lighting and texturing and colors and all that sort of stuff. But if anyone has any questions, let me know. Otherwise, we'll continue on with that, and we'll probably knock that off next Monday. And then you'll hopefully have enough of an idea of 3D graphics to do the assignment, which I'm yet to write. Yeah, any questions?
Drawing shapes, just visuals, what is
How do you mean?
when you draw a cube, do you have to work? Draw a cube, change the measurements, so it looks.
You can. Usually you'd probably just adjust, usually you set up your viewing volume and you just leave it as is, and then, assuming you've set up a decent one, they should look fine. I have read various bits and pieces where people have had to tweak things because they look weird, which is more just, if the viewing volume and the camera setup isn't as we expect things to be in the real world, sometimes things can just look a little bit unusual, but most of the time it should be fine. Most of the time if you say, you know, here is my cube, it will look like a cube in perspective view volume, unless you've done something like set the field of view way too wide, in which case, you know, instead of the camera being able to see like this, it can see like that. It's like looking through a fisheye lens, so everything sort of gets like compressed and distorted. Cool. All right. We'll see you guys on Monday.
Thanks.
No worries. Yeah, have a go through the processing tutorial.